तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we were considering finding out the inverse Laplace transform through the method of partial fraction expansion. We shall continue this discussion with an example. Let us consider f of s, a rational function which is s plus 2 over s plus 1 plus s squared plus s plus 1. This has obviously 3 poles, one at minus 1 and a pair of complex conjugate poles at minus half plus or minus j root 3 upon 2. So one way of handling this would be to make the partial fraction expansion corresponding to the 3 poles. So k2 over s plus half plus j root 3 upon 2 and another term corresponding to the conjugate pole minus j root 3 upon 2. Now it turns out, since this the pole is complex, this will also be a complex number. K2 is a complex number, and since the pole, this pole is the complex conjugate of this, it turns out that K3 will be K2 conjugate. So one way of handling this would be to find out the 3 residues corresponding to the 3 poles. Find K1, which is simple, K2, which is of course complex, and K3 we don't have to spend extra time to find out K3, because once you know K2, the K3 will be K2 conjugate provided the coefficients in the rational function, coefficients of various powers of s in the rational function are real. So in making this partial fraction expansion, once you find K2, K3 can be immediately found out. But then this needs a little bit of complex algebra manipulation. An alternative way of doing this would be to combine these 2 terms and get the result as a fraction, because after all, finally when you find the inverse Laplace transformation, you will find out that when you have a function quadratic factor in the denominator, it is convenient to identify this with the Laplace transform of e to the power of minus alpha t cos omega t type of function. So to do that, let us write this partial fraction expansion as say s plus 1 corresponding to k1, and the second term would be the combination of these 2. It turns out that will be s plus half whole squared plus root 3 upon 2 whole squared. So if we can express this quadratic factor in this form, it will be convenient because we can associate this with a well known time function, as we will see as we go along. Now to find out the residue of the pole at s equals minus 1, you multiply this by s plus 1 and substitute s equals minus 1 in the usual manner, and you will get the result as 1. And once you have that, to find out the term corresponding to the numerator here, you can arrive at a common denominator and identify the numerator coefficients with the coefficients of s plus 2 and find out the numerator here as minus s plus 1. So this is straightforward. I will not work out give the complete details. After having done this, you recall that the Laplace transform of s plus alpha over s plus alpha whole square plus omega squared, that is inverse Laplace transform of that is e power of minus alpha t cos omega t. Therefore we should like to express this as a linear combination of s plus half one term and root 3 by 2 as the other term. If we do that, then we can identify this with the Laplace transform of terms like e power minus alpha t cos omega t and e to the power minus alpha t sin omega t. So to do that, let me write 1 over s plus 1, all right, and the second term s plus half whole squared plus root 3 upon 2 whole squared. Now I must express this as a linear combination of 2 terms like this. So since there is a minus s here, so I will write it minus of s plus half, that is, we can recognize this to be the Laplace transform of e power minus half t cos root 3 upon t 2t with a minus sign out in front, but we have minus s plus 1. Therefore, instead of plus 1 you have minus half, therefore you must introduce plus 3 by 2, but we must express this as a coefficient times root 3 upon 2. Therefore, this will be root 3 upon 2 multiplied by root 3. So that is the linear combination of these two terms that we are looking for. Now we have got the three terms which are known Laplace transforms of particular time functions. Therefore, we can find out the inverse Laplace transform, that is the time function as corresponding to the first term you have e power minus t, corresponding to this term you have minus e power minus t upon 2 cos root 3 upon 2t, and corresponding to this term you have plus root 3 e power minus t upon 2 sin root 3 upon 2 t. So that is the, of course, the whole thing is multiplied by u of t. So that is the inverse Laplace transform of this given rational function. So now we have used here a trick in the sense that we have not found out the residues of all the poles specifically. Whenever you have complex conjugate poles, a pair of complex conjugate poles, it will be convenient for us to find out a term in the partial factor expansion with both these terms together with have a denominator quadratic factor with real coefficients, in which case that can be identified with damped sinusoids in the manner shown here. Now let us continue our discussion with the situation where poles are of multiple order. So far we have considered rational functions where the poles are all simple. So what happens if some poles are of multiple order? In other words, if f of s is Ps over Qs, Qs equals 0 has repeated roots. So some factors are repeated, then we will say that f of s has multiple order poles depending upon the repetition. Suppose it is repeated twice, it is a pole of order 2. If a particular root is repeated 3 times, then we say a pole of order 3. We will illustrate this again by means of an example before we work out use the general rule. Suppose we have f of s equals s plus 2 divided by s times s plus 1 times s plus 3 whole square. So this is an example. We will talk about an example first, then we will give the general rule. Now here we have 3 distinct poles, one at the origin, one at minus 1, and a second order pole at s equals minus 3. Therefore, we have k1 over s plus k2 over s plus 1, and corresponding to this multiple order s plus 3 whole squared in the denominator, you can express this as k3s plus k4, or alternately it suits us to have express this as k3 over s plus 3 plus k4 over s plus 3 whole square, because these are easily identified with the Laplace transforms of well-known time functions. So it would be convenient for us to express this in this manner. We can, to streamline this work, to extend this in the general case, we will put it this way. This pole at 3 has got 2 repeated roots, therefore we have k31 and k32. I will put it in this manner, k31 and k32. Now it is to find out k1, we proceed in the same straightforward fashion, multiply this by s and substitute s equals 0. Therefore s plus 2 over s plus 1 times s plus 3 whole squared with the substitution s equals 0, and that gives me value 2 by 9, no problem at all. Similarly, if you want to find k2, you multiply this rational function by s plus 1, which leads me to s plus 2 times s plus 3 whole squared, and substitute s equals minus 1 because that is the pole at which you want to find the residue, and that becomes minus 1/4. So no problem as far as these two are concerned. Now you have to find out k31 and k32. Of this, k32 is easily found out by multiplying this rational function by s plus 3 whole square, so that on substitution s equals minus 3, all the other terms vanish. Therefore k32 can be found out as, or maybe we will put it, we will illustrate this in a more general way. Let us suppose I write here, multiply this s plus 2 over s times s plus 1 times s plus 3 whole squared. I multiply this by s plus 3 whole squared, so that this term will be cancelled out, and we will call this m of s. So this is m of s. That is, on multiplying this by s plus 3 whole squared, I get m of s. So on the other side, you have k1 s times s plus 3 whole squared plus k2 over s plus 1 times s plus 3 whole squared plus k31 times s plus 1 times s plus 3, sorry, k31 times s plus 3 plus k32. So on multiplying this by s plus 3 whole squared, the terms corresponding to the partial fraction, each term gets multiplied by s plus 3 whole squared. Now if you substitute s equals 3 minus 3 in this, you observe that this vanishes, this vanishes, this vanishes, and leaves with you k32. So k32 is found out again in a straightforward manner by multiplying this by s plus 3 whole squared and substituting s equals minus 3, that will give k32. So we have found out this residue, and this one. When we have multiple order poles, it is actually the term associated with the linear term that is called the residue. This is really the residue of the pole at s equals minus 3, not this one. In mathematical literature, this is called the residue of the pole at s equals minus 3, and that is the one which is harder to find compared with the others. Now how do we find k31? Now the trick in this is, we have got m of s is equal to this. Now suppose you take the derivative of m of s with respect to s, then what happens is this term drops out, and this leaves you with k31. As far as the other terms are concerned, since s plus 3 whole square is a factor here, when you take the derivative of m of s with respect to s, s plus 3 continues to be a factor because it is a quadratic factor. Once you take the derivative, s plus 3 continues to be a factor in both these terms. Therefore we take dms, the derivative of ms with respect to s, the derivative of m of s with respect to s equals k1, I'll simply put, suppose I call this as x of s. I have x prime of s plus k31. And now x prime of s has a factor s plus 3. Therefore you have, when you substitute dms over ds at s equals minus 3 will give me k31. And what is dms, derivative of ms with respect to s? This is after all m of s. So if you calculate that, you have derivative of m of s with respect to s equals derivative of this s squared plus s times 1 minus s plus 2 times s squared plus s, that is 2s plus 1 divided by s squared plus s, and that is what we have dm of s by s. and s squared plus s whole squared, that's right. So dms over ds substitution s is equal to minus 3 will give me, after you work this out, with 1 by 36, and that of course is K31. So the upshot of this is the partial fraction, required partial fraction expansion will be K1 over S, K2 over S plus 1, K31 over S plus 3 and K3 over S plus 3 whole squared, where all the residues are found out. Therefore, f of t will be equal to, corresponding to the first term K1, that is 2 upon 9, 2 upon 9 over S. Therefore, the inverse Laplace transform is 2 upon 9 times ut. Ut will come at the end anyway, minus 1/4 e power minus t corresponding to this term, and corresponding to K31 you have 1 upon 36 e power minus 3t, and corresponding to K32 over S plus 3 whole squared. K32 is found out as we have not worked it out. K32 will be equal to, when you substitute S equals minus 3 here, K32 is found out as minus 1/6. You can work this out, minus 1/6. Therefore, this becomes minus 1 by 6, and since it's K32 over S plus 3 whole squared, inverse Laplace transform is t multiplied by e power minus 3t, and the whole thing is multiplied by u of t. So the final answer is 2 upon 9 minus 1/4 e power minus t plus 1 by 36 e power minus 3t minus 1/6 t minus t, t times e power minus 3t multiplied by u of t. That is the final result. Now, after having worked out an example, let us now discuss this in a more general way. When you have multiple order poles, how do you find the various terms in the partial fraction expansion? Let us look at it in a more general way rather than through an example. Let us now consider a general case of situation where multiple order poles occur. So, given f of s, which is Ps over Qs, let s minus s1 raised to the power of r be a factor of Qfs. In this event, we say that the pole at s equals s1 is of order r, because this particular factor is repeated r times. Then the partial fraction expansion of f of s will have the form corresponding to the pole at s equals s1. We can write this as k11 over s minus s1 plus k12 over s minus s1 whole squared. So the denominator will have expanding powers of s minus s1, and finally you have k1 r minus 1 by s minus s1 raised to the power of r minus 1 plus k1 r over s minus s1 raised to the power of r, plus terms which involve other poles of f of s, plus terms which involve other poles, that is poles other than at s equal to s1. Let me call this group of terms as R of s, because we really, our focus now is on how to calculate k1 to k1r. We are not interested in the other terms. So our discussion will center around methods of finding out k11, k12 or up to k1r. Okay. Now, taking the q from the example which we discussed just now, let me say m of s is obtained by multiplying f of s over s minus s1 raised to the power of r. So this is the partial fraction expansion of f of s. You multiply this by s minus s1 raised to the power of r, then this entire group of terms will be multiplied by s minus s1 raised to the power of r. Therefore, that will turn out to be k11 times s minus s1 raised to the power of r minus 1 plus k12 raised to the power of s minus s1 raised to the power of r minus 2 down the line, plus compared to this last two terms k1r minus 1 times s minus s1 plus k1r plus this entire group of terms r of s multiplied by s minus s1 raised to the power of r. That is how this m of s would look like. So every one of these terms is multiplied by s minus s1 raised to the power of r, and this is what the result is. Now it's easy to see now that k1r is simply found out by substituting s equals s1 in this expression, because every term vanishes except this when you substitute s equals s1. So when you substitute s equals s1 in m of s, k1r falls out. So k1r equals m of s, which is really ps over qs multiplied by s minus s1 raised to the power of r, with the substitution s is equal to s1. That is quite straightforward. That is k1r. k1r. Now to find out k1r minus 1, we adopt the same trick as we have used in this example. You recall, we took the derivative of m of s with respect to s. If you do that, this term drops out, and the derivative of this is simply k1r minus 1, and since these are all accompanied by higher powers of s minus s1, when you take the derivative, they still continue, s minus s1 continues to be a factor here. Therefore they all drop out. So when you have got dm s over ds, if you do that and substitute s is equal to s1, then the only term that remains is k1r minus 1, because k1r disappears, all the other terms have a factor s minus s1. Therefore when you substitute s is equal to s1, that remains. That is k1r minus 1. Now suppose you take the second derivative, then the previous term will come. The previous term here, you recall, it will be k1r minus 2 s minus s1 whole square. So when you take the first derivative, you get 2 times s minus s1. When you take the second derivative, it will be 2 times k1r minus 2. Therefore you have k1r minus 2 will be 1 upon 2 dms over ds, substitute s is equal to s1. As a matter of fact, this is, instead of 2, I will write as 2 factorial, because that is how it progresses. And the previous term, when you take k1r minus 3, you will get in the final analysis 3 factorial. That is how it goes. So continuing this discussion, it is easy to verify. You can show that k1j is obtained as 1 over r minus j factorial. The r minus jth derivative of m of s over with respect to s, with the substitution s is equal to s1. And in fact you get k11, that is the first term here, k11, and this is in fact called the residue of the multiple order pole at s equal to s1, k11, which is the hardest to find out. It is obtained by taking r minus 1th derivative of dr minus 1 ds. So in principle it is the same as what we have done in the first example worked out. Only thing is, when you have got a large number of multiple order pole, you have to take successive derivatives of this term m of s, f of s times s minus s1 raised to the power of r. That is, you knock off the term in the denominator, which is s minus s1 raised to the power of r, and the rest of the rational function you take successive derivatives and substitute at every stage s equals s1. So you get all the terms in the partial fraction expansion starting from k1r right up to k11. k11 is the numerator of the linear factor, k1r is the numerator of the factor s minus s1 raised to the power of r. So the principle is straightforward. You don't have to really remember these formulas. Provided you know the principle that is involved, you can always figure out how it is done. You have to take the rational fraction as such, given rational fraction, multiply by s minus s1 raised to the power of r, and you get a resultant rational fraction function which is called MFS, you take successive derivatives and substitute S is equal to S1. So the principle of finding out the partial fraction expansion when you have got multiple order poles is again a straightforward extension of what you have done in the case of simple poles, and when you have a combination of simple poles and multiple order poles, you have to use a combination of both the techniques. Simple poles is quite straightforward, multiple order poles you have to take successive derivatives of this factor MFS. A combination of these two has to be adopted. And in the case of complex conjugate poles, if you find the residue with respect to one complex conjugate pole, it's enough. The second, its conjugate, the residue corresponding to its conjugate is the conjugate of that residue itself. This is one way of handling this. Alternately, as the example that we worked out earlier suggested, you can combine the terms corresponding to two conjugate poles and find out, have a quadratic denominator and find out a linear factor in terms in the numerator and associate this with terms of the type e power minus alpha t cos omega t and e power minus alpha t sin omega t. That can also be done. Otherwise, if you can leave them as linear terms and then find out the residues corresponding to the complex conjugate poles, find out the inverse Laplace transform of this and combine these two resulting time functions, which again yields finally the same result. Consider the method of finding out the inverse Laplace transformation using the partial fraction expansion. There is another method which is the contour integration, which is more fundamental and which stems from the very definition of the inverse Laplace transformation. You recall that the inverse Laplace transformation ft is 1 over 2 pi j c minus j infinity to c plus j infinity of f of s e to the power of st ds. So in the complex plane, you take the integration along a contour like this, c minus j infinity all the way down to c plus j infinity. Let me say this contour is gamma. So this integration is along to this. Now it's easy to evaluate the integral along a closed contour in a complex plane because from the theory of residues, once you have integration over a closed contour that is equal to 2 pi j times the residues of the poles inside the contour for the complex variable theory. So what one does is to close this by means of two large semicircles where r tends to infinity. Let me call this gamma 1, call this gamma 2. It turns out that if you have this integral, if you have this integral evaluated around this contour for t less than 0, it vanishes. So integral f of s e to the power of st vanishes along this contour for t less than 0. On the other hand, if you take it along this contour gamma 2, this integral f of s e to the power of st ds vanishes for t greater than 0. So since we want to really evaluate this integral along this contour from this point to this point, but nothing is lost if we add to this contour this particular large semicircle for t less than 0 and this large semicircle for t greater than 0. So in other words, I can say this is equal to 1 over 2 pi j, evaluate the contour, closed contour gamma plus gamma 1 of f of s e to the power of st ds for t less than 0, because after all I am adding to that a quantity which is equal to 0, and this is equal to 1 over 2 pi j integral along this closed contour for ds for t greater than 0. And it turns out that as far as this contour integration is concerned, there are no poles inside because all the poles will be here. Therefore, since this closed contour does not include any poles, this turns out to be 0. And as far as this is concerned, this will be equal to the sum of the residues of poles inside the closed contour plus 2. So whatever poles you are having here, you take the residues of the poles, that will be equal to your f of t for t greater than 0. This is equal to, this is for t greater than 0, this is for t greater than 0, this is for t less than 0. So in the inverse Laplace transform, you will get f of t will be identically 0 for t less than 0 because of this, and for t greater than 0 it is equal to the sum of the residues of the poles inside this. Our discussion here has necessarily to be very cursory because this is not the method that we use for normal evaluation of the inverse Fourier transform, inverse Laplace transformation. I'm just giving this to you for the sake of completeness, and the partial fraction expansion is so much simpler, and that takes care of most of our needs. We don't really have to do contour integration, but because this is a basic one, and this will have to be resorted to for special types of functions for which we may not know the inverse Laplace transform simply. So I included this. So we will not pursue this topic. We just mentioned that the contour integration is alternative method for finding out the inverse Laplace transformation. So far we have discussed the definition of the Laplace transformation, its properties, and also the method of finding out the inverse Laplace transformation. You would have noticed that many of the properties of the Laplace transform parallel to those that we have already studied under the Fourier transform method. And we also notice that for certain functions the Laplace transformation and Fourier transform are quite related to each other, in the sense that if you substitute j omega for s, you get the Fourier transform from the Laplace transform. For example, you have e to the power of minus alpha t ut. The Fourier transform is 1 over j omega plus alpha. The Laplace transformation is 1 over s plus alpha. So by substituting j omega for s, you get the Fourier transform from the Laplace transformation. On the other hand, suppose you have u of t itself. The Fourier transform of this is 1 over j omega plus pi delta omega. On the other hand, the Laplace transformation is 1 over s. So here there is a discrepancy. So one would like to know under what conditions will be the Fourier transform obtained by mere substitution of j omega for s from the Laplace transformation, and under what cases will they differ. This substitution will not yield us the appropriate Fourier transform. This is the question which we would like to address. Let us consider three cases. A, in the Laplace transformation, the f of convergence is less than 0. Now before this, it must be clearly mentioned that whenever we compare the Laplace transform and the Fourier transform, we can do it only for the causal time functions, because the Fourier transform integrates from minus infinity to plus infinity in the time axis. So your f of t has values for t less than 0. There is no reason for the Laplace transform and Fourier transform to be related to each other. So whatever comparison we can make can be done only for causal time functions. So the first case corresponds to a situation where the f of convergence is less than 0, which means that fl of s has all poles in the left half plane. Examples: e power minus alpha t ut has Laplace transform 1 over s plus alpha. Example A. B, e power minus alpha t cos omega naught t will have the Laplace transform s plus alpha over s plus alpha whole squared plus omega naught squared. That means here all the poles will be in the left half plane. In all these cases, we have this the Fourier transform f of j omega is obtained from the Laplace transform of the corresponding function with the substitution s is equal to j omega. So we have the Fourier transform can be obtained from the Laplace transform by the mere substitution of s by j omega. Conversely, the Laplace transform is obtained from the Fourier transform by substituting s for j omega. So when the absence of convergence is less than 0, Fourier transform and Laplace transform are very closely related. One is obtained from the other by substitution of s for j omega or j omega for s. Suppose I have the abscess of convergence to be greater than 0. That means there are some poles in the Laplace transformation of FL of S in the right half plane. So maybe you are having some poles here. So that means that's why the abscess of convergence is a positive number. Example of such situation will be t to the power of 2t ut will have the Laplace transform 1 over s minus 2. Now all we can say is for such functions Fourier transform does not exist because the integral does not converge. You have f of t e to the power of minus j omega t dt. That integral cannot converge because you have an exponentially increasing time function. In such cases Fourier transform does not exist. So there is no way in which we can relate the Laplace transform and Fourier transform. Simply Fourier transform does not exist for such functions. The third case will be when the abscess of convergence is equal to 0. That means there are poles of FL of S in the left half plane and on j omega axis. On j omega axis. The abscess of convergence is 0 because you have poles on the imaginary axis as well. Example, ut 1 over s cos omega naught t s over s squared plus omega naught squared. So all these are cases where you have poles on the imaginary axis. What do we do in such cases? The general rule is FL of S in general will have FA of S which has got all poles inside right half plane, inside left half plane, plus some poles which are on the imaginary axis. Let us say bk over s minus j omega k. So it will have bk over s minus j omega k, where k, the summation is on k. That means the Laplace transform FL of S can be thought of as the combination of the terms which correspond to poles on the imaginary axis plus terms which do not involve poles on the imaginary axis, which have all poles inside the left half plane corresponding to case A. In such situation, it can be easily visualized that the Fourier transform of this will turn out to be, by substituting j omega for this, FL j omega, FLS s is equal to j omega, plus corresponding to each one of these poles on the imaginary axis, you have got bk pi delta omega minus omega k. bk pi bk delta omega minus omega k summed on k. So it turns out that in such situations, for every pole on the imaginary axis and the corresponding residue, you have an extra delta function, and that is why when you go to u of t 1 over j omega pi delta omega you are getting. The corresponding residue here is 1, so pi delta omega you are getting. So this is what it will be. So to summarize then, whenever you have the absence of convergence less than 0, then the Laplace transform and Fourier transform are very closely related. Substitution s equal j omega will get one, you can require one from the other. But if you have poles on the imaginary axis, you have delta functions in the Fourier transform, you don't have delta functions in the Laplace transformation. We will close this discussion of the properties of Laplace transformation at this stage, and in the next lecture we will continue with the Laplace transformation in the application of Laplace transformation technique to system analysis and circuit analysis. But now I think it's an appropriate time to break at this point and look at an exercise on the topics that we have already discussed relative to Laplace transformation. The first question is, find the Laplace transforms of the set of time functions that are given here. A, t squared e to the power of minus at ut. B, t plus 2 whole squared times u of t minus 1. So this time function really starts at t equals 1 onwards. The third function, time multiplied e to the power of minus at, t e to the power of minus at multiplied by u of t minus t, a delayed step function. So once again, this function starts from t equals capital T onwards. It's truncated for values of t less than capital T. D, e to the power of minus 5t times hyperbolic cosine cos 3t ut. We have not talked about Laplace transforms of hyperbolic functions, but you can always express them as the sum of exponential functions and then combine this with e to the power of minus 5t, and you can find the Laplace transform of that. D, e, t e to the power of minus t sin t ut. Here again you have a combination of these factors. We have worked out examples where e to the power of minus t sin t, we found the Laplace transform, but that multiplied by t. So whenever you multiply by t, it's equivalent to taking the derivative in the transform domain. So you have to use those properties to find the Laplace transform of this. F, given that f of t has the Laplace transform of f of s, what would be the Laplace transform of another function derived from f of t in this manner, e to the power of minus bt times f of t minus b. So it's scaled by a factor b. In addition, you have multiplied it by an exponential term, e to the power of minus bt ut. Take b to be a positive number and then find this out, find the Laplace transform of this in terms of b and f of s. Then we are given the waveforms of two time functions. One is an aperiodic function. This is all the function there is for outside this range from t equals 1 second to 4 seconds it is 0. So within this interval t equals 1 to 4, it behaves in this manner. It linearly rises from 0 to 3 units and then climbs down to minus 2 steeply and then remains at minus 2 from 2 seconds to 3 seconds and then once again comes back to 0 at 4 and stays there for t greater than 4. So it is an aperiodic function described in this manner. H is a periodic function. The variation for one period 0 to t naught is prescribed as here. It starts from a and comes down to 0.8k in half a period linearly, and then it jumps to minus 0.2a at this point and again increases linearly and reaches 0 at t equals t naught. So this is the basic variation in one period, and using the find the Laplace transform of this variation in one period and then use the property of Laplace transforms for periodic functions to find out the Laplace transform of the entire time function. As a second example, we have listed here a set of Laplace transforms. Find the time functions to which they correspond. That means find the inverse Laplace transforms of A, s plus 2 over s squared plus 8s plus 15. B, s plus 1 over s plus 2 whole squared times s plus 3. That means there is a repeated pole here. So you have to use the rule for finding out the residues when repeated poles are involved. C, 2s squared plus s plus 1 over s times s plus 2. You observe here that the numerator has the same degree as the denominator. Therefore, apart from the factor which correspond to k1 over s plus k2 over s plus 2, you also have a constant term 2, which is the ratio of the two leading coefficients. So 2 plus some k1 over s plus k2 over s plus 2 is the partial fraction expansion of this. So corresponding for the 2, the inverse Laplace transform will be 2 delta t. So whenever the numerator degree happens to be the same as the denominator degree, you have a constant term in the partial fraction expansion, and in the inverse Laplace transform you have a delta function. D, you have 4s plus 5 over s squared plus 2s plus 10. These lead to complex conjugate poles. So instead of finding out the residues of each of the complex conjugate poles, you can do it. That is one way of doing this. Other way would be to treat this as s plus a whole squared plus omega squared, and then try to find out the inverse Laplace transform in terms of cosine and sine functions with an exponentially decaying amplitude. Then you have 2s plus 1 over s plus 2 times s squared plus 1 whole squared. Here you have repeated poles on the imaginary axis, slightly more complicated, but you can handle this in the same way as you have done earlier. Then f s plus 2 over s squared plus 8s plus 15 times 1 minus e to the power of minus 4s. In tackling this problem, you already know the inverse Laplace transform of s plus 2 over s squared plus 8s plus 15. So all you have to do is use this information here, because e to the power of minus 4s means whatever f of t you had obtained here is the same f of t delayed by 4 seconds is what corresponds to this. Therefore, use this information that you already obtained here to find out the f of t corresponding to this. 1 over s, 1 plus e to the power of minus s. So if you had 1 minus e to the power of minus ts, we recognize this to be the Laplace transform of periodic function of time. So all you have to do is multiply both the numerator and denominator by 1 minus e to the power of minus s. So you have 1 minus s, 1 times 1 minus e to the power of minus s by s times 1 minus e to the power of minus 2s. Therefore, you can recognize this to be the Laplace transform of some periodic function, with the Laplace transform for the basic period being 1 minus e to the power of minus s over s. You can find that out. Similarly here you have e to the power of minus pi s by s squared plus 1 e to the power of minus pi s minus 1. So if you multiply both sides, numerator and denominator, by minus 1, you have 1 minus e to the power of minus pi s. So you can remove that, then find out the Laplace transform of the remaining function, and once you introduce that, it becomes the Laplace transform of periodic function of time. So using all the properties that we have derived, you find the inverse Laplace transforms of all these 8 functions of s. Question number 3, you have a capacitor in a circuit, current I is the current passing the capacitor, and Vc of t is the voltage across the capacitor. Suppose to the solution of this network we found out the Laplace transform of the voltage across the capacitor Vc of s. Let it be in symbolic form a1s plus a0 over s cubed, a1s plus a0 over s cubed plus b2s squared plus b1s plus b0. That is the Laplace transform of the voltage across the capacitor. Now, using this information in terms of a and b constants, find the final value of the capacitor voltage Vc infinity. B, the initial value of the capacitor voltage, which is Vc 0 plus immediately after t equals 0. Also find out the initial value of the current I 0 plus. And lastly, find the initial value of the derivative of the current I prime 0 plus. This means this is di by dt evaluated at t equals 0 plus. So this is an application of the initial value theorem, final value theorem, and the derivative rule. All these are needed for solution of this problem. In other words, you don't have to explicitly find Vc of t. Using this initial value theorem, final value theorem, and the derivative rule, you should be able to find out all these quantities in terms of the a constants and the b constants. Question number 4, use convolution theorem to find the inverse Laplace transform of 1 over s plus 1 times s plus 2. Verify using the partial fraction expansion. So this Laplace transformation can be thought of as the product of 1 over s plus 1 times 1 over s plus 2. You can find out the time functions corresponding to these two factors, and since it is the product that is involved in the transform domain, in the time domain it is a convolution. So it is a convolution of the time functions corresponding to 1 over s plus 1 and 1 over s plus 2. Find out the corresponding time function. Now you can also find out the inverse Laplace transform using partial fraction expansion, verify using partial fraction expansion, and compare the two answers. Both of them must naturally agree. So this is an exercise in not only partial fraction expansion but also using the property of convolution. Question number 5, you are given two time functions. F of t is a pulse which lasts from 0 to 2 seconds having an amplitude 1, and g of t is an exponentially decaying time function e to the power of minus tt ut. Find ft star gt, that is the convolution of ft and gt. Both are causal time functions, both are amenable to Laplace transformation. Find this down in time domain, purely working out in time domain from the basic definition of the convolution integral. You find out ft star gt in time domain. As an alternative, verify using Laplace transform. In the second step, what you have to do is find the Laplace transform of f of t, find the Laplace transform of g of t. Since we are interested in the convolution of these two, that whatever is the result of this convolution must have for its Laplace transform f of s times g of s. So you find the Laplace transform of this, find the Laplace transform of this, both are simple to find out. Find the inverse Laplace transform, you get ft star gt. Lastly, you have the error Et of a controlled quantity in a control system has for its Laplace transform this expression E of s equals s plus 1 over s plus 1 whole squared plus 4. The error Et of a controlled quantity in a control system has for its Laplace transformation E of s plus 1 over s plus 1 whole squared plus 4. Without explicitly finding E of t, you don't have to find the inverse Laplace transformation of this to find E of t. Without explicitly doing that, evaluate E infinity, that the final value of this error. B, integral 0 to infinity of Et dt, the integral of that error over the period 0 to infinity. C, 0 to infinity T Et dt, that is time multiplied T Et dt. This you should be able to do it without actually finding out E of t using initial value theorem, the rule for integration, and so on and so forth. You can also extend this to ask you to find, I can ask you to find out integral 0 to infinity of E squared t dt, that is the integral of the square error, but that requires a convolution in the complex domain. Since we have not discussed that, we have not included that type of question. So this exercise covers the various properties of Laplace transformation that we discussed in the earlier 6 lectures. In the next lecture, we will discuss the application of the Laplace transformation technique to evaluation of transients in networks and systems.